In the previous video, we've learned how to compute the value of each state under the policy imposed by ourselves. But the greatest power of the Bellman equation is that it allows us to solve reinforcement learning tasks and obtain the optimal policy even for very complex environments. In this video, we will solve the Bellman equation iteratively and arrive at optimal policies for arbitrary 2D grid worlds. In this animation, you can see one such iterative process of the policy updating itself and eventually becoming the optimal policy. The states marked with the black dots reward the agent with the +1 reward, so they are the desired target to move towards. And the state marked with the cross returns a -1 reward, so it's being avoided by the agent. And once we have the algorithm ready, you will be free to locate these positive and negative rewards any way you'd like. And the coding solution that I'll teach you in this video will be ready to tackle your arbitrary environments. But first, let's think about what characterizes the optimal policy, denoted pi star. This policy is not optimal because starting in some states leads the agent to receive the -1 reward. This is the policy that we've been using in the previous video. This policy is also not optimal because in those states over here, they lead us nowhere and the agent ends up receiving no reward. So the value of being in those states is 0. But this policy is one of the optimal policies because from any starting state, it gets us to the +1 reward. And not only that, it gets us there in the smallest possible number of steps. Looking at these three possible value functions, we see that the optimal policy will always be the one which maximizes the value of every state. In this case, values are the maximum we could get for this environment. We will now apply the Bellman equation iteratively until we obtain such value function that indeed every state in the environment has the maximum value possible. Then it will be pretty straightforward to compute the optimal policy that is associated with this optimal value function. And by the way, how many possible policies are there for such 2D grid worlds? Well, the general formula is this. It's the size of the action space to the power of the size of the non-terminal state space. For this very small grid world, we have 4 actions and we have 22 non-terminal states. So this will be 4 to the power 22, which is approximately equal to this number, 10 to the power 13, which is a huge number of possible policies. And yet in this video, we will be able to find the optimal one pretty quickly with our algorithm. We will use an algorithm called value iteration. We'll use our Bellman equation, but to keep things simple, we are still going to assume that all state transitions are deterministic, so we don't use the state transition probabilities. And here's the algorithm. We're going to initialize the value function matrix to zeros, and we are now going to iteratively update values in that matrix with the Bellman equation. In each state, we loop over all 4 actions and update the value function for that state to whichever action maximizes the value of the next state. And this procedure is guaranteed to converge as long as the discount factor gamma is less than 1. Here's the example iterative process of updating the value function matrix in each state. You can see that the values of each state get updated to more and more accurate values that sort of propagate from the value of the state that rewards the agent with the +1 reward. So we begin by defining all the prerequisite. We import Numpy and we specify the discount factor gamma. We specify the size of the environment and the location and the numerical value of the rewards. The black dot will denote the target associated with the +1 reward, and the cross will denote the state with the -1 reward that should be avoided. This time though, we also have to define what actions are possible in this environment because we want the algorithm to test all of them in every state, because we start off with the assumption that we don't know which action is the optimal one in each state. And we have 4 actions: go up, go down, go right, go left. And note that the action go up is defined with this movement vector -1, 0 that subtracts an index from the vertical direction. And this is because of how we indexed the array that defines the environment. So a vertical index decreasing means the agent is moving up. And the last thing that we define here is a list of all possible state locations. The entries in this list are 2-element tuples that contain the indices along the vertical and the horizontal direction in the environment. And this will be useful at the time when we need to loop over all possible states. We are simply going to loop over each element in that list. The rewards function is the same as in the previous video. We give the non-zero rewards in the 2-terminal state, and everywhere else the reward is 0. And note that you could also implement a small negative reward everywhere else, say -0.01. And that way the agent would get penalized with every step taken in the environment. And this is sometimes done in reinforcement learning to promote fast movement of the agent towards the target. And it may change the dynamics of how the agent collects the rewards. And I will show you an interesting application of this later on in this video. Unlike in the previous video, we no longer specify a function with an imposed policy. Instead, we simply code a function that executes an action in a given state. So this function takes the current state and the action selected as arguments, and it returns the next state. And we model the 2-terminal states where no more future actions are possible from those states, so the agent just remains there. And for every other non-terminal state in the environment, we simply add the action vector to the state. And this action vector is selected from this actions array that we have defined earlier. And finally, over here, we make sure that the action does not cause the agent to leave the environment. So we clip the next state to remain within the environment. So this whole function essentially programs the movement of the agent over our 2D grid world. And now's the time when we program the value iteration algorithm. We initialize the value function matrix to zeros. We specify the convergence threshold, which is going to provide the condition for terminating our iterative search for the optimal value function. And here's the iterative search. The delta over here is a matrix that will store our measurements of how much update we've made to the value function with each iteration. And we first loop over every state in the environment. If the state is terminal, then we hard code the value of that state to be the immediate reward received in that state. And over here, for every state, we also loop over every possible action. In other words, we test each action in each state to see which one will maximize the value function. So also, this is where we compute the Bellman equation given the current value function, which initially does not provide an accurate estimate of the optimal value function. So also, its updates are not accurate. But with time, this is guaranteed to converge to the optimal solution. So this whole procedure over here updates entries in this value function matrix. So with each iteration, we get closer and closer to the optimal value function. And specifically, because we are always aiming for whichever value was maximum, this algorithm converges to the optimal policy, which by definition maximizes the value of each state. And this last bit over here is testing how well are we converged. We measure the absolute difference between the old value function and the new, if the maximum of that difference is less than a convergence threshold, then we break the for loop and terminate the algorithm. So this whole piece of code essentially accomplishes this. It will iteratively converge to the optimal value function for this environment. And before we go any further, let's pause for a moment and see what we've accomplished thus far. In the previous video, we've learned the value function, vpi, for an arbitrary policy that was imposed by us. In this video, we've now learned the algorithm that lets us compute the optimal value function, v star, without us having to impose the policy. And we know that the optimal value function is present when the agent executes the optimal actions, so it has to be associated with the optimal policy, pi star. And now the last thing that we'd like to do is to retrieve this optimal policy given the optimal value function. And we can do that simply by retrieving the action in a given state that results in that particular optimal state value. And this, as you might anticipate, will involve another series of iterating over all possible states and over all possible actions in those states. So let's do that now. We initialize the policy matrix to zeros, and this matrix will contain integers that for every state tell us which of the 4 actions, 0, 1, 2, or 3, we need to execute. We now loop over all possible states. If the state is terminal, then we don't associate any action with it. So we just set the entry in the policy matrix to none. And for every other state, we loop over all 4 actions. And with the Bellman equation, we test which action would maximize the value of that state. Now, the Bellman equation gives us the true value of each state because we're already using the converged estimate of the value function over here. And this part of the code is a comparison of values associated with each of the 4 actions, and whichever is the largest, we will set that action in the policy matrix. Now, if we print that matrix, here's the final optimal policy that was populated with this piece of code. And recall that action 3 was to go right and action 0 was to go up. So let's draw our final optimal policy. Here it is. We are indeed moving towards the target from every state in the environment, and we are avoiding the -1 reward. And this is the policy that is associated with this optimal value function. And we should appreciate what we've accomplished here. I mentioned before that there are 4 to the power 22 possible policies, even for this very small environment. And yet we have found the optimal one, and on my computer, this only took 10 iterations of the value iteration algorithm. And of course, now you can modify the code to create larger and more interesting environments. And the last thing that I wanted to show you is a fun extension of our value iteration algorithm applied to this new larger environment, where what I've done is I've placed 2 targets, one associated with the +1 reward and the other associated with the smaller 0.1 reward. And here I'm showing you the optimal policy found for this environment. And notice that this small reward, even though it's positive, it's not being taken by the agent. And this is because there is this larger reward waiting for the agent over here. So even in those states surrounding the 0.1 reward, the agent essentially knows that it's beneficial to go grab the big reward instead. But if I modify this problem a little bit and I penalize the agent for taking every step in the environment by a very small but negative reward, -0.01, then you can see that the agent starting in those bottom right corner state actually goes to take the smaller reward. And this is precisely because every step in this environment costs us some. So in the long term, the expected return on the reward isn't so great if we have to travel a long distance over this environment. And even more so, this behavior will also depend on the discount factor, gamma. So here it was 0.9, but if I decrease it a little bit, meaning that the future rewards are even slightly less important in this summation over here, then we get this as the optimal policy. So there's an even larger batch of states where the agent decides to be satisfied with the smaller reward. And this is precisely because we've discounted the future rewards some more. And this shows us that both the way that the rewards are placed in an environment and the discount factor, gamma, can alter the dynamics of the growth mindset that our agent has. And in fact, we could say that he still has a growth mindset in this environment. It's just that he makes a very calculated decision for what is going to profit him the most in the future. In the next video, we will look closer into some theory of the Markov decision process, MDP, and we will move towards handling those transition probabilities, which we have so far been happily ignoring. See you then.